Okay, this is where we stopped last time, so let me just quickly review. So we have a DFA fixed, so we have deterministic finite automaton fixed, and we are supposed to construct the NFA. And remember how we did this yesterday, that we had the DFA, a particular DFA in question, and we constructed an NFA by just starting at the start state and looking to the where we're supposed to go by just looking at NFA. If there are a couple states that are possible from a given state, then we collected them in just one single state, and we just named them. Let's say from Z0 you go to Z1, Z2, you name a state Z1, Z2. So, and this was basically a power set construction. What we really did is, for states, I can take all possible subsets of Z. So these are the names of my states. So the names of my states are now Z1, Z2, Z3 can be a name of my state. So every possibility is possible. I start at the start state, and the most importantly, how do I transition? If I'm sitting at Y is some subset, let's say Z4, Z7. Then where do I go from Z4, Z7 when I read A? Is I look where I go from Z4, I look where I go from Z7. This may be a couple possibilities because we're looking at the NFA, and I collect them all together in a single name. This is what this thing says here. And then an accepting state is all the states such that the name of the state includes the accepting states from the original guy. Okay? Come on. Right, let me open this up completely and then I'll zoom it in. So now I have to prove something, right? What do I have to prove? I have to prove that this constructions, when I do all possible subsets and the transitions between subsets, actually works. This amounts to proving the following thing. By the way, this is the notation. So we know the notation for a successor configuration without the zero. So we know that K prime is the successor of K if blah 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 things hold. We can define the nth successor. By the zero successor, I will just mean that they are equal. And by n plus 1 is I apply this thing n times. So this is just a notation. This n here stands for it's n steps taken on the NFA, basically. So, and my claim is, so recall that this is m prime, by the way. M prime is a DFA. M is an NFA. So what I'm claiming is that if I have a DFA, so I construct my DFA with this, whatever I mentioned how to construct it, with this power set construction. So I constructed it, and let's say I constructed my DFA by gluing these things as we described, and I start at Z0, Z0 prime is the start state, and I read word W. This says that after n steps, I end up somewhere, right? So if, should we do an example again? I don't want to do it again because we did it basically yesterday somewhere. Here we did this yesterday. So let's say I made n steps and I started at Z0 and I'm at Z1, Z2, Z0. So this is my Y now. So I end up at Y, and I still have to read some tail of my word. But here is the claim. Y has the name, right? Y is just the name of different states. 1, 2, 3, let's say. Z1, Z2, Z3. Y exactly consists of those states that are reachable by NFA from Z0. So Y, so if I make, so what this says, that if I make n steps in my DFA that I created, this is and I end up somewhere, right? This thing has a name. It has a bunch of different Z's as names, so a bunch of different states. These are exactly the states that are reachable in my original NFA by taking n steps. This actually proves the claim because the end states, remember what the end states are? End states are the ones that contain the End states are named as ones that contain the real end state. Well, the NFA end state. And exactly what this claim would show is that those end states are reachable, basically. If you start at Z0 and you end up at somewhere where you included an end state, that means that in the original end states, if I prove this, after end state, I can reach the end state. So it's a little... So, yeah. So the state y, this is what it says here. The state y after n step of a deterministic computation is the set of all states reachable by n step by non-deterministic computation. And this, of course, proves the claim because you exactly reach the end states this way. And you have to stare at this for a moment. If you see this for the first time and you have not looked at it at home, this might be confusing. I understand this. But we prove this by induction on n. Right? N is the number of steps you're making. If n is 0, this thing is trivial because you're not making any steps. And if n is 1, this is also actually very easy. And I'm just going to tell you what it is, and I will leave for you to actually... This is the whole point. That I assume, I start at Z0, and I assume that after n steps, this is the place I end up with. So... And I'm just assuming that after n steps, this y, by induction hypothesis, consists of those states that are reachable by n steps in a non-deterministic computation. This is an assumption. And then I just make one more step. And essentially, by construction, how I do this is a union over all these guys here, which again is exactly what I want. So there is actually a very trivial thing going on here. It's somehow, the complication is hidden behind the notation, basically. So I'll just go over, I'm not going to tell you anything more about this. Stare at this at home and ask questions next time if you like. But this is basically not complicated. It's just proven by induction, and you assume this and just make one more step. And just use the definition of delta star. By the way, if you were to construct this from, maybe that was a better idea to actually think about why would I want to do it, but that's besides the point. Actually, this proves the claim. So let me remind you what we actually proved here. What we proved here is that if I have a non-deterministic finite automaton, I can construct a deterministic finite automaton M prime, which accepts exactly the same language. So non-deterministic automata, even though it seems like it's more complicated, it's really not. Okay? There will be exercises on your worksheet as well to actually construct a DFA from the NFA. Oh, by the way, let me ask you the opposite question. Let's say I have an DFA. How to construct an NFA from the DFA? So if I go here, so let's say I have an NFA, right? Only difference between NFA and DFA is that this function here, delta, goes from z cross a to 2 to the power z. And I want to construct a function now, delta prime, that goes from z a to z. How would I do this? So exactly, by the way, in the recording I said, so we have the D prime, we have the DFA, and we want to construct the NFA. And how do we construct it? If I have the given DFA, how do I define delta? Delta, let's say, ZA is defined as whatever delta, like this here. So I will define this way. It is a set of delta prime ZA, which is just a single guy. This is just a single state, and this is supposed to be a set, so it will contain a set that contains just a single guy. This is just a nomenclature. There's nothing special going on here. Okay. So we continue now, basically. So I leave it up to you to find out the details here, but Rather, I would actually now, what I want to do is I want to even improve my NFA even further. So what can my NFA do? It can read a letter and it can go so it has a choice to go many different directions. Now I'm going to give it even more power to read nothing and make a move. These things are called epsilon moves. So what this basically means, so if I go here, let me scroll down. So now I'm going to draw an NFA that can make an epsilon move. So here, let's say it's in state Z7 for simplicity. And let's say there's like this, and then it's, I don't know, something 4. So there's some kind of NFA here, like this. Let's say it's an NFA. This is part of an NFA. What I'm allowing it to do is to read epsilon and go to Z8. That means, let's say my alphabet is now, again, 0 and 1. So my alphabet is just 0 and 1, so it can read zeros or ones. But what this guy can do now, and let's say my input is coming in, let's say the 1 is here, and let's say 0 is here, and then this continues again somewhere here, like 1, I don't know, and 0. 1, and let's say there's 0 here. So let's say it's an NFA like this, and let's say the input is coming in 1, 1 is my input, and my state is in Z7. So my machine is here, I'm in state Z7, and I'm reading 1, 1, let's say, like this. What this epsilon can do, it can jump to state Z8 and then read 1, 1. So the next, I want to be able to do this, to go to Z8 and still be able to read 1, 1. So you can think of it this way, like the Z7, 1, 1, right? So this was my configuration. This is somehow the same, let's write it this way, as Z7 epsilon 1, 1. This is correct, right? Epsilon can always be inserted. It does nothing. It's an empty string, so it does nothing. So you can think of 1, 1 as epsilon 1, 1. And then in this case, I want to make it possible that Z7 reads epsilon and maybe goes to Z8. So when Z7 reads epsilon, it goes to Z8. So the next configuration can be maybe Z8, but the input is not read. Now it is not possible as we constructed NFA, because in every state you have to read a letter and produce possibly many different states. But it cannot just not read the letter here. It has to read 1. I mean, you have to have 1 going somewhere here, right? As we constructed it now. But I want to improve my NFA. And these are called epsilon moves. Epsilon moves are your machine, without reading an input, can spontaneously change the state. NFA-ია და რომელიც გაუსწორდება. So if it has just this 1, so the question is what happens that it has 1 coming out here, and maybe it goes to some, I don't know, Z27, so the completely different thing. And it reads 1, 1. Does it go here and then read 1, 1, or does it go here? Either one. It's an NFA. It can go like this or like this, and I say that the input is accepted if the accepted computation exists, either here or here. It's the same exact thing as we did. This might also happen, right? 1 might go even somewhere else because it's an NFA. So epsilon does exactly the same thing. So now you really have 3 things connected to Z7 instead of like this. So this is what I want to do. In order to do this, what I do is I modify my definition of an NFA. So far I had that for every state and for every alphabet letter, I produced a set of states where I can go. Now I add epsilon. So A is my alphabet, so A epsilon is A added epsilon. So I have my 0, 1, let's say, I also have epsilon, and now my state function space is for every state and for every letter or epsilon, so letter or epsilon, I produce a set of states. And delta Z epsilon means all possible states where I can go by reading nothing. So if my state is Z like this, so my state is Z, and I have epsilon goes to many different states, there might be a bunch of epsilons coming out like this, right? Then I can spontaneously jump to that state without reading anything. I'll show you why this is tremendously helpful with an example. Why this is so powerful. Well, let's say I have a DFA. Let's say I have a DFA like this. I don't know. This is a start state, and it goes like ... And then let's say this guy is called M, and let's say I have another DFA like this. This guy is called M prime, which does different things. Okay? So this DFA M, or NFA, sorry. This NFA M accepts some language, right? So let's call this guy LM. This is the strings that this guy accepts, and this is the string that this guy accepts. Can you construct an NFA that accepts the union of these two? Can you construct an NFA that accepts, right on off top of your heads, this language? So exactly the NFA that accepts strings that M accepts, and also the strings that M prime accepts, and nothing more. So your answer, everybody's answer is correct. What you're supposed to do is create a new. You create a new starting set. So your starts what's it called? Start state. These are no longer start states, so I erase them so they do not have two circles. And what I do is I connect them like this, and these are epsilon moves. I do this. What this means, when I start here, I can appear here or appear here without reading an input. If I have no epsilon moves, then I have to write some letter here, and that means I'm already reading something, and that is not good. So if this machine accepts, then this machine will automatically start here, jump, and accept. If this machine accepts, it can jump here and accept. So this new machine that connected with epsilon will automatically accept things that M accepts, M prime accepts. So exactly this, basically.
But doesn't that mean that M and M prime are the same language? Because if it jumps to the wrong DFA, NFA, and the language is not accepted there, how does
Yeah, the thing is, remember how we defined that NFA accepts something?
Yes.
It's defined that if there exists a correct jump. So if, let's say I have a string X that is in LM, and you're saying that what happens if it jumps here instead, right? However, if it jumps here, the computation does not succeed. But if it jumps here, it succeeds. And my definition is, if there exists a successful computation, I say that it accepts.
Cool. It's not DFA.
So no, this is not a DFA. This is an NFA. Yeah, exactly. Yeah. So this is I'm making NFA more powerful. This is what I'm doing. So it was NFA to start with. It has two epsilons here. Rogor. Okay, so this. Oh yeah, that's actually a mistake. Yeah. I'm sorry. It was supposed to. Yeah. This is completely wrong. I was supposed to write. I meant starting state, and now when I was circled, we circled the accepting state. I meant this. It was like this before, and now it's like this. This is what I meant. Accepting state, I don't care. Yeah, maybe somewhere here. and maybe somewhere here. This new machine will have accepting states, which is the union of this guy and this guy. Exactly. Any two NFAs, you can combine them this way and get a union. You can also get an intersection, well, not intersection. You can also get a concatenation, and you can also get a star. That's the whole point. Okay, we'll get to that, but this is clearly visible that this is powerful, and I made a mistake. Instead of two circles, I meant the arrow.
We can connect two or more, like three NFAs can connect like this?
Of course, yeah, you can connect as many as you like. You will have an epsilon move with many different. Delta Z epsilon will connect 5 sets, 7 sets, whatever. And yeah, how I redefine, remember I wrote down this K epsilon 1, 1. Now I can, how the semantics is redefined, basically. What is the next computation now? I allowed more things. Before I had that, if I have a next computation, I have to read the head W. I have to read the first letter. But now what I can do is if I have a configuration that in state Z and I'm reading word W, I can move to state Z prime but not read anything. This is a crucial thing I can do, but I only can do this if Z prime is in delta Z epsilon. So it's connected by an epsilon move. That's what it says. If Z prime is connected to Z by epsilon move, I can go from Z to Z prime without reading anything. This is what it says. Okay, so now the simulation actually becomes harder. Now, see what I did now? So what I did is basically I had an NFA, and in the previous example, I created a DFA out of the NFA, right? And I said it's the same. But now I'm saying I have an NFA that has even more powers, like epsilon moves. Can I create a DFA now? That is my question. Now, if in addition my NFA also has epsilon moves, it's even stronger. Can I construct a DFA in the same exact way? It turns out you can, and let's show you why. Let's show you why this is true. So simulation of an NFA by finite automata becomes harder. So this is what we had in the power set construction. We had that the start state was Z0, and if I want to go from state Y after reading A, I just look at all possible states I can get from Y with one step, and I take their union. This was before. But now I need to also account all the epsilon moves that I'm making. So let me explain to you this, try this in English. So let's say I'm sitting in state Z, right? So maybe let's draw this. Unfortunately, I do not have my stylus today, and that's why I'm struggling with drawing. Let's say I'm sitting at state Z. I'm sitting here at state Z, and before I had like NFA, so I had maybe it goes like this, and like this. This goes to state A. Let's call it, this goes to state B. Let's call this goes to state C. Let's say this was a snapshot of an NFA. Before, how did I construct a DFA, right? The DFA I constructed started with, it would have something like this, and then it will have just one here, and here I will have a set that has A, B, and C. This is what we did before. So all three were collected into one. But imagine now I also have epsilon moves. What should I do if I have an epsilon move and I go to state D? Where should I go from here? I somehow should be able to, without reading anything, I should be able to move to D somehow. Exactly. This is what you're supposed to do, what you're saying. So maybe I have like F here. I have to just add to Z all the possibilities where I can jump to with an epsilon move. Because I can jump there somehow and then read the input. So let me show you what I mean, and maybe you'll see more clearly. So that is why I'm doing this construction now. It's called, I have to augment everything by states reachable by epsilon moves. So what are the states reachable by epsilon moves? Let's say I have a collection of states. Think of it just one state for example in your head. For a toy example, think that Q is just one state, Z. So let's say Q is just one state, Z. By E0Q, I just denote Z. It's nothing. What is E1Q? E1Q will be all union of all states that are reachable by epsilon moves from Z. So what I did in this case, if this is my snapshot, let's erase this guy for a moment so we can draw here. In this case, E1 of Z will be F and D. This is supposed to be F. Damn it. So E1 includes all the states that are reachable by just one epsilon move. But it might be that then there is yet another epsilon move that takes you to, I don't know, K. Then from Z, I can, with 2 hops, go to K as well. See what's happening? So it doesn't really matter how many epsilon hops you make, it's still one epsilon somehow. Without reading anything, you can hop from Z to D, then hop to D to K without reading an input. And maybe then this somehow, maybe this goes then here with an epsilon move, and then it just then cycles. So E1 is just one epsilon move, E2 will be 2 epsilon moves, E3 will be where can you get with 3 epsilon moves. So basically, this is what it is. E0 is just the Q itself. Q can be many different states, but think of it one state. E1 will be union of all things you can get from Q with an epsilon move. E2 will be after the second epsilon move, third epsilon move. And what I'm claiming now, and I'm asking this question, is that I have to at most make Z, however many states I have, minus 1 many epsilon moves, and everything is already reached what can be reached with an epsilon. So let me reiterate this in that. So what I'm claiming is it can happen that by epsilon move you go there, by next epsilon move you go there, and by next you come back. And then if you do it again, you just go like this all the time. And what I'm claiming is that if you do however many states you have, minus 1 many times, the union, if you increase your Q 1 time, twice, 3 times, you go by epsilon, 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 then at some point, you will not increase your EQ anymore. All of the states will be in there. And your argument is basically correct. You run out of states. And by EQ, I call that union after I make Z minus 1 steps. This will be all states that are reachable from Q with epsilon, as many epsilon moves as you want. So EQ is basically all reachable states by epsilon moves. And how I change my machine, my NFA is what you said. My start state will not just be my start state, but rather a start state and all states that are reachable by epsilon moves. And my transitions will be the same thing, the same transitions of the union of the sets, plus all the states that are reached by epsilon moves. But not just one epsilon move, but as many as I like. We will do this more in the exercises. I actually went fast today because we were too slow. So what does E? So Q is a set of states. any, say, Z7, Z8, Z9. So 3 states. EQ, let's say we don't know what we did here. I'm just going to explain what EQ does, and let's say you believe me. What EQ does, if Q is just 3 states, EQ includes all possible states in your machine that can be reached from these 3 states with epsilon moves. Not just one, but any number of epsilon moves. So EQ will include all states in your machine that can be reached from states of Q with epsilon moves. So if you only use epsilon jobs, where can you go? All of them are collected in EQ. Now, again, I'm doing the same exercise as before. I had an NFA and I'm building a DFA. It's the same exact DFA we built there. So it's the same exact DFA, like the same exact DFA we built here. This same, like this. However, if my initial NFA had epsilon moves, what I have to do is I have to, as you said, I have to add states. I have to add states here like Z7, Z5, if these 2 states are reached from Z0 with epsilon. So you add things here, and here also in Z1, Z2, you just add many different things. You can. So you just add E here and add E here. So this just includes all possible places that you can get with epsilon moves. So here's the question that you. So why are we doing this? So this looks like a bunch of abstract nonsense. So why are we doing this? And it turns out you have seen it somewhere already. This epsilon moves, you had it in one of the classes. Computer architecture or OS or somewhere. So let's explain where we are now. We have 4 minutes and I will explain where we are now and we prove it. It's going to be so apparent. So if you were not listening before, listen now. So where are we now? So our main goal was this, that if you have a regular language L, I wanted to prove that there exists a DFA. This was my goal. I proved one way that if I have a DFA, I proved this, well, rather easily, this direction. I proved that if I have a DFA, the language it accepts is regular. Now I want to go the opposite direction, like this, that every regular language is. I have to construct a DFA that accepts just a given regular language. My strategy is the following, that instead of constructing a DFA, it's easier to construct an NFA. So I will construct an NFA which also has epsilon moves. And I know that these 2 things are the same. I know that if I have an NFA with epsilon moves, I can construct a DFA by the construction I just showed you, this power set constructions plus including the epsilon moves. So I'm going to start with a regular language. And I'm going to construct an NFA which has epsilon moves. And this is the same as constructing a DFA, and the proof will be finished. Now, how would one go about constructing an NFA for a general regular language? Say my regular language is given. So my general L is given. So my L is a regular language. If the language is regular, I know that I started with letters, I did their concatenations, I did their star, and I did their union. So I'm going to construct my NFA with epsilon piece by piece. So what I mean is like this. So let's say L is given, and let's say my alphabet, let's say just for simplicity's sake, is just 0 and 1. So this is my alphabet. Can you give me an NFA or DFA, NFA let's say, give me an NFA M such that L of M is just 0. accepts only single string 0 and nothing else.
Just the state that goes into itself. No, but then we are.
So there's the alphabet is 0 and 1. So this is my start state. Where do I go from 0 with 0?
Just some other state that's an accepting state.
Okay, so I guess you're guessing correctly. So I will go here. I make this an accepting state and I put 0 here, right? This is what you mean. And where do I go with 1?
We have a 1.
Yes, we have 0 and 1.
I guess into itself. No. But then it accepts it.
Then it accepts 1, 0.
Yeah. Well, nowhere. We got different language, no?
No, we can do something like this, right? And then maybe like this. So if it reads 0, it goes here, for example, and it accepts. If it reads 1, it goes here, and then anything it reads, it just reiterates here, and it never comes back. So this only accepts 0. You can do this for any language and any alphabet, that you can always accept one letter exactly this way, right? Okay, now this accepts 0. Let's draw the guy that accepts. ხო, ერთსალ ნულიას. მეც არაფერს. აი ეს ბოლო აუცილებელი ხო? თავის თავში რა არ შეიძლება საერთოდ არ. არა, DFA თუ მინდა NFA-ში ჩათვალე რომ ცარიელი სიმრავლე გაქვს, მაგრამ იყოს DFA. ორივე უნდა იყოს ერთიანის და ნულიანი, ყველა DFA-ში კი. მაშინ რასაც უნდა. Yeah, this one should, yeah, you're right. This one should go like this. Right? You're correct, yeah. This is the correct description, yes. So it accepts 0 and everything else comes here and then it stays here forever. In NFA you can have delta Z A be empty. Well, empty set. So God damn it, I cannot draw. So it's empty set like this. You can have it. And that means that it goes nowhere. Because this is also a subset. But in a DFA, you have to draw this. You're correct. Yeah, I forgot to draw 0, 1 that go here and 0, 1. So this only accepts 0. Let's say I have another guy here. The same exact guy. Like this. Like this. Same exact guy. But in this time, it accepts just 1. This accepts 0, this accepts 1. Can you build me an NFA that accepts 0, 1? Okay. NFA. NFA with epsilon moves. That accepts 0, 1. This accepts 0, this accepts 1. Can you build me the one that accepts 0? Only that. Exactly. So the one we create a new start state and we just take epsilon moves like this that we did before. This is just a union. And I erase the start states here and here. What is the mugami, guys? So what is the gist here? The gist is that every regular language is constructed by taking unions, taking concatenations, and taking stars. And you start with single letters. I did construct a DFA that accepts single letters. And you know how to construct a union of two DFAs. If I show you how to also construct concatenation of two DFAs, and if I show you how to construct a star, that means I showed you how to construct an NFA with epsilon moves for any regular language. So how would I prove to you that any regular language has an NFA with epsilon moves, or a DFA, which I know is the same? I will show you that there is a NFA or DFA, whatever, for single letters. I will show you that there is, if I have two, I can construct for a union. If I have two, I can construct for concatenation. And then if I have a language, I can construct a DFA that accepts star. Yeah, that's exactly what strategy is. And of course, I know that I can construct for single letters, and I know that every regular language is just single letters, concatenations, unions, and stars. And if I do concatenation, unions, and star, let me just ask you a quick question then. Can you, let's say I have a DFA, let's say an NFA, I draw it this way, so some NFA, some complicated, and another NFA. So this accepts this language, this accepts this language. Can you construct an NFA using, again, epsilon moves that accepts this language? Concatenations of the strings.
We just add epsilon moves to each step.
So this, let's say this one has a start state here. This is my start state here. This one has a start state here.
We just add epsilon move from each state to the start of the other language?
If you do it from each state, it might jump without accepting the string. So it's moving, and it's, let's say, decides to jump and then decides to accept, and you will accept something that is. So what are the strings here? The strings here are x, y's, such that x is accepted by this guy and y is accepted by this guy. Ho, to ti arapel. Sustad, so exactly, you're right. So if this has many accepting points, maybe like this also, all of them will go with epsilon moves, will go to the start state, whatever was the start state here, and now I will only accept if I go here, and then I can jump, and the new accepting states have to be what? Achali accepting state romeli ikneva. Exactly, that's it.